Here we're going to be taking a look at example problems using the mean value theorem. Feel free to stop the video at any time in order to go through the actual algebraic steps. You also can refer back to the other video I've made on the mean value theorem explaining it in more detail. So the mean value theorem says that if a function f is continuous on a closed interval a to b and differentiable on the open interval from a to b, then there must exist some value c in between a and b such that the slope at c is equal to the slope of the secant line over the overall interval a to b. So, given the function x squared on 0 to 2, f is a polynomial, so it's continuous and differentiable for all values of x, so therefore it has to satisfy the mean value theorem. So let's find the value c for which it works. So, we've got that f prime of c is equal to f of 2 minus f of 0 over 2 minus 0. So I'll take the slope over the whole interval. I'll find my derivative, plug in c, set those two things equal to each other, and I find out that a value of c equals 1 is a point which works. Now c is definitely on the interval from 0 to 2. So let's see, we've got a visual example here supporting that rationale. So we've got our two endpoints, 0 to 2. I've drawn my secant line. In my solution, I calculated the slope of my secant line. And then I found that there is a point c in between those two endpoints, such that the slope at that point is equal to the slope over the whole interval. So in other words, the slope of the tangent at the point is equal to the slope of the secant line connecting 0 to 2. On our next example, we have a piecewise function here, and so we notice that both of the branches themselves individually are continuous and differentiable for all values of x, and so therefore we only need to check the differentiability and continuity of where they actually meet up together. So in other words, where x is equal to 0. For a function to be continuous at a point, the limit as you approach that point must exist, the point must exist, and those two values must equal each other. So I take the limit from the left, and that's 1. The limit from the right is equal to 1. So therefore the limit exists and is equal to 1. The height at 0 is equal to 1. Therefore, since these are the same, f is continuous at 0. Now, for it to be differentiable at a point, the slope as you approach from the left and the slope as you approach from the right must be approaching the same thing. So we look at the left branch. I find its derivative, which is negative sine of x. And then the derivative of the right branch is cosine of x. I take the limit of the left branch as we approach 0 and the limit of the right branch as we approach 0, and I examine those slopes and what those slopes approach. And I see that the slopes approach 0 on one side and 1 on the other side. Therefore, f of x is not differentiable at x equals 0. Now, while it is continuous, but it is not differentiable, this means that the mean value theorem doesn't guarantee there has to be a value c on the interval. But we might get lucky. So let's take a look at our graph here. So I graphed my first branch, and I graphed the second branch, and then we have the secant line over the whole interval from negative pi to pi. And while the mean value theorem doesn't guarantee the existence of a value of c, it looks like we get lucky, and there are actually two different values of c which end up working. So let's go ahead and then now calculate what those two values of c would be. So I go through the same process again. I find my slope over the whole interval, which is 1 over pi, and I set my derivative at c equal to 1 over pi. So I do that for the left branch and the right branch, and I see the two different values for which that's true, and both of those values work on their own branches. The first value that I got is indeed between negative pi and 0, and the second value for the second branch is indeed between 0 and positive pi. So although the function does not satisfy the hypothesis of the mean value theorem, there ends up being two values of c which satisfy the conclusion. The key here was that there was no guarantee that they would have to exist. Now, our third example, we have a semicircle. So it's going to be continuous and differentiable everywhere except for the endpoints, because at the endpoints you have vertical tangent lines. But luckily we don't need to worry about the differentiability of the endpoints with the mean value theorem. So once again I go through the process of figuring out my slope of my secant line, so my average rate of change, which turns out to be 0 in this case. because my height at 1 and negative 1 are both 0. And then I'm going to calculate what my derivative is and set that equal to 0. So using the chain rule, I get that my derivative is 1/2 times that quantity to the negative 1/2 times negative 2x. A little bit of simplification, and I get the following derivative. I plug in c, and so now I have those two values equal to each other, and the place where this derivative will equal 0 is the place where the numerator is equal to 0. So in other words, c will be equal to 0 at 0, which indeed is on the interval negative 1 to 1, as guaranteed by the mean value theorem. So let's take a quick look at what this looks like graphically, just to help us visualize our algebraic stuff there. So you can see that at the endpoints we've got tangent lines that are vertical, undefined, but we don't need to worry about them. So let me go ahead and show the secant line over the interval. It has a slope of 0, and yes, at 0 it has a slope of 0. So we have our point C, guaranteed by the mean value theorem.